All right, so I'm going to be talking about building test-check generators. Some quick metadata. My name is Gary Fredericks. I live in Chicago. I use Clojure at DRW, and I spend some of my time working on improving test-check. So I'm going to try to put this in the context of the broader Clojure ecosystem. Test.check was created 4 years ago by Reed Draper. It is a Clojure library for property-based testing, somewhat like the original quick check in Haskell. And that means that it lets you write properties that describe things that should be true about your functions for any input, and then test those properties on randomly generated input. So if you're doing that, then probably you're spending a moderate amount of your time describing the inputs to your functions, also known as building generators. Alternately, clojure.spec was announced 18 months ago, and one of its major features is integration with test.check, which means that when you have specs, especially basic specs, it can create the generators for you and then test your functions automatically. But because a spec can be an arbitrary function, this means that users will have to eventually supply their own generators when things are complex enough. So one way or another, people are building generators, and much like functional programming, it can be a little bewildering to beginners. So I'm going to try to address that with this talk. So the roadmap here is we'll start off talking about generators in general. So we'll look at what's available and why it is the way it is. Then we'll look at one big example of building a substantial generator. And then finally, we'll talk about fine-tuning things. OK, so to start off with, let me identify what namespaces I'm talking about. So we have the two libraries I mentioned earlier, test.check and clojure.spec. Test.check on the right has some namespaces for running tests and integrating with other frameworks, that sort of thing. But it has a nice little partitioned or quarantined namespace for the generators on the bottom right. Spec also has a namespace for specs and another namespace for testing things, and it has its own generators namespace, and this is mostly just a proxy to enable dynamic loading of test-check. So whichever side you're using, you're probably going to be encountering the generators namespace on the bottom right, and that's where this talk is going to be focused. So it should be useful to people coming from either direction, and for the most part, I'm not going to talk about this distinction anymore. So we're just going to be in the bottom right. So let's look at what comes out of the box with test.check. These come in basically two categories. They're the basic data generators. These are all, I think, not too weird. We've got our traditional scalars like booleans and numbers and UUIDs, et cetera. There are functions that take arguments and return a generator. So the vector function on line 4 it takes a generator for elements and returns a generator for vectors. So the sample output on line 15 is a vector of integers. There's a function called elements on line 7 that takes a collection of values, and it will give you a generator that just picks randomly from that collection. So you can see on line 18, we just picked one random color. There's also a tuple generator so that you can generate collections that are heterogeneous. So if you pass in, say, 2 different generators, it will generate you a pair where the first thing comes from the first generator, the second from the second. And then the whole expression here is a call to the hash map function on line 2, and you pass it the key value pairs with keys and generators for values, and it will generate you a map with the same keys taking the values from the corresponding generators. So I think all of this is not too intimidating, hopefully pretty intuitive. But the other category of generators are what I call the combinators. And these, at first glance, are pretty weird and declarative and smell like monads. And so I think it's a little bit like when you first encounter functional programming. So I want to try to justify why it is this way. So we'll have a little more appreciation. So if you think about how you might try to design a generator without knowing anything about the problem, just the first thought, it might be a function, takes no arguments, and returns a random value. You can write this using one of the random functions inside of Clojure core. So we call the random function on line 3. We get a random number, and we generate this assertion about a favorite number. So when we now have a favorite number assertion generator, and we can call it by just calling a function with 0 arguments, and it returns one of the values we wanted to generate. So this is good, but test.check, one of the features it has is it likes to start a test on very small inputs and slowly grow the size of the inputs. So it needs some way to tell the generator what size it wants. So the way test.check does this is with what we call the size parameter. It's sort of an abstract idea of size. It's implemented as just a number from 0 to 200 or so, and the generator gets to interpret it however it wants. So in this case, we could just take the size as an argument and then use it to determine how big of a number we use in our favorite number assertion. So we can pass the size to the randint function. That'll sort of bound how big of a number we get. And so now we have a generator that we have to pass a size to when we call it, and then it'll return a value. But another feature of test.check is that when it finds a failure, it wants to be able to incrementally shrink the value in order to find a simpler version of that failure. And you might think that it could do this all on its own, and it's not part of the generator. But on line 7, we have this string, and if this was failing our test and we wanted to shrink it, it's not really obvious without knowing anything about the generator what a valid way to shrink it is. For an arbitrary string, you might be able to just take out characters or reduce one of the characters to some other character. And most of those things are just not valid on this string. The only valid way to shrink this string is to shrink that number on the right-hand side of it. But only the generator knows that. And so the way test.check's implemented is that the generator needs to return not only a value, but also a description of all the different ways that you could shrink it from that point and the subsequent points. And so this is implemented as a lazy tree that I haven't even tried to code on here because it'd be kind of a headache. But you could imagine doing it if you're good at this sort of thing by writing a recursive function and lazy sequences and all that. So now we have a function that takes a size and returns 2 different things. But wait, there's more. When you run tests, especially random tests, you want to be able to do it deterministically. And because of the way test.check is implemented, it's useful to have an immutable random number generator. So we have to pass that in as well. So we now have 2 arguments and 2 return values. And this is maybe like bordering on the verge of doability if you need to like write your own generator. But this is just generating like one thing. What if you needed to generate a collection or some other heterogeneous thing, and like now you need to combine all these different inputs and merge and split and all sorts of headachy stuff. So the reason that test.check has these really abstract combinators is because it supports all of these different features. It supports growth, it supports shrinking, and it supports determinism. So one thing I want to mention real quick is that there's also these dev tools in the generator's namespace. These will show up on later slides. Sample, you can pass a generator and get some small samples from it. And the generate function is very similar, but it just gives you one thing instead of many. But I realized when I was thinking about this that I've said already that for a beginner, test.check has similarity to functional programming, where it's a little intimidating. Things are weird in a way that like don't seem like they need to be so weird. But with practice, they get a little easier, and you can appreciate them a bit more. In particular, some similarities are the universality. In functional programming, you can express anything using a functional program, and similarly with these generator combinators, you can generate anything, even though it's not obvious at first that that's possible. And it takes practice before you can sort of think about how to use them that way. It's also tempting to circumvent them, just like with functional programming, especially in a dynamic language. You can use trapdoors and have mutation or whatever it is that you need. And sometimes that's justifiable. And especially with more users coming from spec, there seem to be different use cases for using generators that really tempt people to use these impurities. And I'm not going to say you're a bad person if you do it, but I think you should at least know that you're undermining the different features of test.check. So if those features aren't important to you, you can do whatever you want. But this talk is going to be focused on not circumventing those features, like how to build generators and keep those features. So now I'm going to go through the different combinators in a little more detail so that when we have our big example, they'll be a bit more familiar. So the first one is the tuple generator. This was also on the basic data generators slide because I think it can work both ways. But the signature is you pass in a variable number of different generators, and it will give you a generator of tuples where it takes one thing from each generator. So this is a way of generating several things at the same time. Another generator with a very similar signature, the one-of generator takes a collection of generators and then returns a generator that just picks from one of them randomly. So sometimes you'll get a triangle, sometimes a circle, etc. The frequency generator is very similar, but gives you a bit more control over the distribution. So you can pass in a weight to associate with each generator, and that'll determine how often it picks from each one. Next is such that. This takes a generator and a function. So if you have a generator of triangles and then a function that takes a triangle and returns true or false, this is essentially a way of filtering. It will give you a generator that only generates things that pass that predicate. I'll talk about that a bit more because it's a bit tricky, but for now we're going to move on. The fmap generator, this one is super useful, also takes a generator and a function. This time the function takes the thing generated as an argument and returns something else. And they get combined together, and you get a generator that generates whatever the function returns. So this is a way of essentially adding some post-processing to a generator. If you have all the information you need, but it's not in the shape you want, you can do these arbitrary transformations. So this is very useful. Bind looks very similar at a glance, except the arguments have been swapped. And so I'm going to put them side by side. The only real difference, aside from the confusing argument switch, is that the function in bind needs to return a generator rather than a value. So it seems like it may not be like a very meaningful difference, but it's actually a big leap in complexity and power. So I'm going to dig into that a little bit because I think it's worth understanding. So let's imagine that you wanted to generate a non-empty collection and a random element from that collection. So you could start by doing the easy part. Let's generate a non-empty collection. So we can do that on line 6 and 7 by just using the built-in generators. And then we're going to pass it to fmap. And so now we have a function that takes one of those collections we just generated, and we want to maybe figure out how to pick a random element and return that. So one way to do this is to cheat. You can call the randinth function in Clojure core with your collection and make a little tuple with the two pieces and return it. And if you run this generator, it will work, or at least it looks like it works. And it certainly does work fine for generating things, but you're missing some of the three features from earlier. So let's try something else. We could use the elements generator that we saw on the data slide. So on line 7, we'll take our collection and pass it to the elements function. And that gives us a generator that'll pick a random thing, which is what we need to do. And we can pass that to fmap on line 6 and take that random element that was generated and wrap the two of them up in a vector, which we could do lexically from the context. And so this expresses all of the logic we need. But when we run the generator down at the bottom, we get a generator and not a value. And this makes sense because with fmap, your function's expected to return a value. And what we actually returned on line 6 was this fmap generator. So anytime that you're tempted or you need to return a generator from your fmap function, that essentially tells you need to be using bind instead. That's exactly what bind is for. So this slide is just like the last slide, except the arguments have been switched, and we are calling bind instead of fmap now. And this actually works, but it's a little bit hard to read. So fortunately, we have a macro in the generator's namespace called let. This is based on the Clojure core let, except now paired up with names, we have generators, and so the names refer to the values generated from the generators and not the generators themselves. So in line 2, we have our non-empty collection generator, and we give a name to the collections being generated, and then we can take that collection and pass it into the elements generator on line 4, give a name to the random element x, and then wrap those up in a pair. And so this does the exact same thing as the previous slide, but it's hopefully a bit more readable. Another example real quick, if you want to generate a 2D matrix, the easy thing of just using two nested calls to a vector is not quite going to work because then the inner vectors will have just random lengths that don't match each other. So an easy way to do this is, again with bind, but using the let macro. On line 8, we generate a small non-negative integer for the width, and then use that to assemble our generator of vectors. So now we can fix the inner vectors to have a fixed width, and they will all match. This wraps up the first section. I talked about the different generators. We have basic data generators and the abstract combinators. The abstractness it's difficult, but it's in service of something that I think is valuable. And like functional programming, it gets more familiar with practice. So our next section, this is going to be the big example. So this example is inspired by Benjamin Pierce's keynote from 2 years ago, where he talked about testing a Dropbox-like system. I'm not going to worry about the mechanics of how you test something like that. I'm just going to think about what things might you want to generate if you were doing something of that sort. So let's say we want to generate a nested directory of files and some changes to that directory. So if you're going to do this, you probably want to generate file names. And test.check has a string generator built in, and you might have the opinion that a file name probably shouldn't have slashes in it. So how can we generate file names without slashes? We can take that string generator and pass it to such that, and have a predicate that checks whether there are any slashes in it or not. And if you try this out, it will work. You pass it to sample, you get some nice file names that don't have slashes in them. But if you sample it a little harder, then you'll eventually run into this exception that I assume a lot of people have seen, that such that could not find a string that didn't have a slash in it after 10 tries. And this happens because once you're generating large enough strings, they're highly likely to have slashes. Or at least they've got a decent chance. And if you do that over and over and over again, you'll eventually, just by bad luck, run into 10 of them in a row that all have slashes. So such that is really only appropriate if your predicate gets more likely to pass as you look at larger and larger examples. And that the opposite is happening here. This comes up a lot for spec users because of the and spec. Because the only way to generate something from an and spec is to generate something from the first spec and then pass it to such that and check that the other specs pass. But fortunately, most uses of such that can be replaced with a clever use of fmap. So the example in this case is you can just generate a string that might have a slash and then use fmap to pull out all the slashes. So your generator is going to be doing a little bit of extra work and throwing things away, but that's okay. So if we pass this to sample, we get more nice file names that don't have slashes, and this one will actually never throw the such that error. We also might want to generate file contents, in this case byte arrays, and test.check has a byte array generator built in, so we can just use it. We alias it on line 1 to gen file contents, and then we can pass that to sample and see lots of nice random byte arrays. We might also want to generate metadata. And just to make this interesting, let's say that when we generate the permissions on a file or directory that we want it to be in the octal format. So there's not any sort of obvious built-in way to generate octal strings in test.check. But you could just generate the underlying number that's represented by an octal string, which is a number from 0 up to the largest 3-digit octal number. So whatever that is, and the reader will figure it out, but we can pass that to the large integer generator to get a number in that range, and then use fmap to format it as an octal string. And fortunately, the format function built into Clojure knows how to generate octal strings in one line. And so we get a generator that works pretty well. Another part of metadata is timestamps. There's nothing built into test.check that deals with time, because time is pretty contextual. But it's not too hard to get a minimal thing going yourself. You can generate an integer that you interpret as a Unix epoch value and just use fmap to pass that into a constructor of whatever type you're interested in generating. So if we do this, we get a whole bunch of timestamps that are all several milliseconds off of midnight 1970. Which is a little weird, and I'm going to come back to that later on. But for now, this is definitely generates some timestamps. So we can wrap these up in a metadata generator, add on some user IDs and group IDs for fun, and we'll get this generator that generates a map with 5 entries. And that's pretty good. Next, we want to be able to generate an actual recursive structure that represents the directory, the file names, the directory names, all that sort of stuff. So test.check has a recursive helper built in, and I'm not going to spend too much time on this because it's a little subtle, but you can, when you use it on line 11, you need to give it two things. One is a generator for the leaves of your tree structure, and in this case, the leaves are the byte arrays. So we'll use our existing gen file contents function for that. And you also need to give it a function that can take a generator for child nodes and generate the appropriate structure at that point. So we'll use this function at the top that takes an argument on line 2 for the content under that thing, and then returns a generator, which is a map from file names to a little 2-entry map that has the metadata and whatever content gets generated by this generator that was passed in. So if we run that on a modest size, we get this very large output. The top level structure, this is a map that has some directory names in it, like equin and shoe underscore, which are good directory names, and they have their own metadata, and they also have content, which is yet another nested directory. In this case, on line 8, we have a file named right parenthesis. It has its own metadata, and it has the contents from the byte array generator on line 13. So let's stash that away for future use. Finally, our top level goal was to generate a directory and changes to that directory. So how would we go about doing that? Well, we could separate this out. We already have a directory of changes, or I'm sorry, we have a generator of directories, and we can make a function that takes a directory and returns a generator of changes, and then combine those somehow. So let's start from the top level on line 5. How would we write this function, assuming we have the function above it? Well, generating first the directory and then the changes sounds like a two-stage thing, which is exactly what bind does. So we're going to start by calling bind and passing in our directory generator on line 6, and then we'll have a function that takes the directory, and it needs to call the gen changes. So we do that on line 11, and we pass that into fmap, and we wrap the things up in a map, and we get back into this not very readable code situation. But just like before, genlet applies. We can rewrite it. So the top is the same as the bottom here. On line 10, we take our directory generator, get the directory, pass that into gen changes. Now we have changes, and we can wrap them up into our final product. So that just leaves this gen changes function that we haven't written yet. For simplicity, I'm just going to talk about generating one kind of change, because there's lots of ways to change a nested directory of things, and I don't have a lot of time. So let's just talk about a change where you append some bytes to a particular file. If we have a generator that can generate one of those, then we can pass that to genvector and get a vector of changes. So how might we generate an appendtion, which I promise is a real word? Well, we can do this in 4 steps. We can take our directory and get all the file paths, and then pick one of those randomly, then generate some random bytes to append to that file, and then wrap them up and return them. So the first step, the file paths, we can write a function that just takes a directory and does a little recursive walk that I'm not going to get into, because this is some regular data processing code. But assuming it works, we can pass the directory that we saved from earlier into this function on line 10 and get a sequence of file names where the slashes have been added in between the directory names and the file names. So if we have that, we can wrap this up into our gen file appendtion function. We call that function on line 3 to get all the file paths, and we pick one at random on line 8 by using the elements generator. We also generate some random bytes on line 9, and we combine both of these things with the tuple generators, so we want to generate them in parallel. And then we use fmap to pass them into a function that will wrap them up in a map for us on lines 5 through 7. So we can use the directory we saved earlier. We can pass it to this function on line 12 and then generate something from that generator, and we'll get a random file path and some random bytes. So back to the top, we have the gen changes at the top that we wrote earlier that will generate a vector of file appendtions, and we have our very top level directory with changes that calls the directory generator and the changes generator and combines them together. And then we can actually try this with a very modest size of 3 so that it fits on the slide. And we'll get back a very small directory that has just one file, which has the empty file name and contains 0 bytes, and we've generated also one change to that same file of adding 0 bytes to it. So that is the giant example I was going through. I don't think that you can get comfortable with this stuff after watching 5 minutes of slides, just like with functional programming. But hopefully I've convinced you that these sorts of things are possible. And as you practice them, they get easier. So last section, fine-tuning generators. So let's first talk about what you might want to fine-tune in a generator. I think these basically in two categories. There's the distribution and growth, and then there's the shrinking. So I'm going to focus mainly on the first one. So distribution and growth is a little tricky to talk about because of the size parameter. So this diagram here shows a sampling of values from the large integer generator at different sizes. So you can see near the bottom when we start out with size 0, the values are clustered around 0. As the size increments, they start getting farther and farther away. But even up at 9, they're still somewhat clustered around 0. They just reach farther to the edges. This is a heuristic that a lot of the test-check generators have. But what this demonstrates is that you essentially have a distribution for every size. And even though they look kind of similar, they're just like scaled versions of each other. They don't have to be that way. And this is only for generating a single scalar. Once you're generating something more complex, it's even harder to think about what the distribution is. We should talk about what size means exactly. So the meaning is essentially determined by how the test runner in test.check uses it. When you run tests, it will start the first trial by generating a value of size 0, and then the next trial it uses 1, and then 2, and all the way up to 199. And then it cycles back to 0 and starts counting up again. You can control what the maximum size is, but that just changes the length of the cycle. So it'll still go up to that max size and then back to 0. And I prefer not changing that and just letting it do this and writing generators with the assumption that 200 is supposed to mean the largest thing you might want to generate on any given day. And since there's ways to control sizing within the generators, this should be sufficient. But before we get into that, the way size is used here has a few gotchas that I want to highlight. One is that if you are running less than 200 trials in your test, then you might not be testing with as large of values as you thought you were. Another is the sample function. When you call sample, you are getting values that are sized from 0 to 9. So if they look small, it's because they're supposed to be. And that's not necessarily what's being tested most of the time. And the generate function uses a default size of 30. OK, so now that we have this little more precise way of thinking about the size of a generator, a common dissatisfaction you might have is that you and your generator disagree about what big means. So if you're generating vectors of strings, for example, you might call the generator with size 10 and see this output and think that this is pretty good, this is about as big as you want for whatever sensitive domain you're using, but that when you call it with size 200, this is just unreasonable, and you would never want to test this, and maybe your test would never return whatever your particular issue is. So fortunately, there's a scale function in the generator's namespace. This lets you pass in a generator and then a function that will transform the size that the generator uses. So you can take this generator that has really big stuff at size 200, but stuff that you like at size 10, and just divide the size by 20. And then you'll get another generator that at size 200 has the stuff you like, and below that, it's even smaller. And obviously, this function can do whatever you want. It doesn't have to just be division or multiplication or something like that. So you can do fancier things as well. This is a good time to mention that there's an open issue in test.check about how collections are sized. Test.check does it kind of naively in a way that results in very large data if you are composing, if you have nested collections that you're generating. And I think spec has kind of increased the occurrence of this problem because it makes it so easy to generate big things. So this is something that needs to be worked on. I hope that it will be fixed in some way before the next release. But for now, it's just you need to pay more attention to sizing. So another category of things that you might have opinions about with respect to your generator is that the stuff it generates is too weird, or it's not weird enough, or some other variant of this. So One example is our file contents generator from earlier, where we were just generating random bytes. If you're testing a file syncing service, then you might suspect that there might be special handling around text files. And so you want to make sure that you're testing text files. But a random byte generator, once it's generating big things, is highly unlikely to generate any valid text files. So this brings up the question, like, how weird should a generator be? I think there's a trade-off here. Like, one of the value propositions of test.check is that by testing lots of really weird things, it's going to find bugs that you weren't even thinking about. And so by like focusing the generators on just generating happy little things that that fit the tests you have in mind, you're sort of losing out on that. But it's also important to test things that you know that your domain is sensitive to, and some generators might just either have zero probability of getting there or just a very low probability. So I think there's a balance here, and there are tools for balancing them. One of them is the one-of generator. So in this case, we can make a generator that half the time generates random bytes, half the time generates UTF-8 bytes, assuming we can write a generator that does that. You can combine them together with one-of and get the best of both worlds. Further, you might notice that the generator only generates small files. So the bytes generator just uses the size parameter as the cap. And so by default, you're only going to be testing on files that are up to 200 bytes. And a file syncing service might well have bugs that only manifest with larger files. But you don't want to use larger files all the time because your tests will be slow. So there's another tactic we can do here. The frequency generator will let you do things that you want to cover but not too often. You can do them not too often. So we can generate bytes or UTF-8 bytes 90% of the time, and then 10% of the time we will generate big files, but only if the size is greater than 100. So I'm not going to go over that in detail, but it's definitely something you can do. Another example of distribution issues is the datetime generator that we looked at earlier. So one of the issues here is just part of the sample function. When we call sample, we're only getting things sized 0 to 9, and so for this generator, they're all clustered around 1970, but for larger values, they're going to be all over the place. Some of them will be 6 or 8 digit years, which is an interesting problem. But even so, they're not really, we're just generating a number. The number doesn't know anything about the different fields in our datetime, and so all the semantics are kind of lost. So there's different downsides to that. And a solution is to actually generate the different fields that are part of the datetime. So this generator has the 7 different fields for the different parts. And if we write a function that can take those 7 values and actually construct an instance of the class that we want, here we have some handling to do for when the day is too large for the month, but we just do something dumb like replace it with 28, which works. And then you combine those two things together with fmap. And we now have a generator that's, it's not centered on 1970 because I just added 2017 to a small integer here. But also you can see that even for small values, the fields are kind of varying in a more natural way. And this also extends to shrinking. When the underlying generator is actually matching the semantics of what you're generating, it can shrink the different fields independently in a way that wouldn't work if you're just generating an integer, because it would just be shrinking the integer, and the different fields would be changing in sort of random ways. So the last section is shrinking. I just talked about shrinking with respect to these to date times and what happens when you model the domain a little more closely. A couple other random things. The UUID generator that's built in turns shrinking off completely. There's a no shrink function that you can pass a generator to get something that just doesn't shrink. This is useful for UUIDs in particular because it means that users can generate UUIDs and assume that they are different, because it also uses a uniform distribution. So it's as random as it is in real life. And then when you're shrinking, they don't all shrink to 0 and start colliding with each other. And it would also take a lot of effort, shrinking time, to do that shrinking. And hopefully your program doesn't have bugs that only manifest with certain UUIDs. But if they do, you can write your own. Okay, the last example is how bind relates to shrinking. So I've talked about bind as being a generator that works in phases. You generate one thing, you call the user function, then you generate another thing. This matrix example that we saw earlier works that way. First we generate the width, And then we have to call the user function to get this vector generator, and then we generate the actual vectors. Bind is very difficult to shrink in an inherent way, because you can shrink either the earlier generator or the later generator. And shrinking the later generator is kind of easy. But if you shrink the earlier generator, you now have changed the thing that was passed into the user function. So you have to call that user function again, get a brand new generator return, and the only thing you can do with it is just generate a completely new random thing from it. And that means that in the case of the matrix, when we're trying to shrink our matrix, we can remove rows from the bottom really easily, we can remove rows from the top, et cetera. But to actually reduce the width means that we generate a totally new matrix with that width. So you can see things where, like in the matrix example, you'll shrink to something that has these sort of trivial, shrunken, degenerate columns that you didn't need. And this can manifest in other sort of situations as well. I don't think there's an awesome solution to this that I know of. If you know of one, please tell me. But this is just something to be aware of when you're using bind. Custom shrinking in general is something that test.check doesn't really support. I'm not sure if there's a good way to do this. If there is, then it could certainly be added. But I also don't think that this is very severe. This is kind of a graceful degradation. In the worst case, if things don't shrink the way you want, you at least have a failing case that you can do something with, even if it's not as small as you'd like. So summarizing this section, things can get too big or small. We have functions for scaling. We have functions for modifying the distribution. You can model your domain a little more directly and get some benefits both for generation and for shrinking. But shrinking in general is kind of tricky. Okay. So this is basically my last slide. Covered a whole bunch of stuff really fast. I apologize for the things I glossed over or said too quickly. But we've covered different kinds of generators. There's the data generators, then there's these abstract declarative things, and building generators. It can be difficult because of this abstractness, but it supports some valuable features like growth and shrinking. And just like functional programming, with practice it gets more familiar. So that's all I have. I think I have a couple minutes if anybody has any questions. In the back? So the question was about base cases like 0 or an empty string or 1970. I think this chart here sort of also gets at the question. So a lot of the generators do have this sort of simplest case that they'll generate if you give them a small size. They'll just start with that. And they will also sort of center around that. Like even this large integer generator, when you get up to size 200, it's going to be generating the full range of 64-bit integers, but it's still going to generate 0 and single-digit numbers pretty often. And that's a heuristic. You can obviously write your own generators that don't do that if you don't like it. The assumption is that lots of edge cases center around these simpler values. And this also means that even when you're generating a big structure, a lot of the leaves will have these simple values. So it's not just that like you'll only get bugs when you're testing tiny things. You'll be testing edge cases even on larger structures. So I think that's part of the justification for that. One more question, Eric? So the question is about custom shrinkage with an example from John Hughes where he shrinks certain operations to a pause. Yeah, that does sound pretty custom. for just the pause, I was going to mention that the frequency generator will shrink to earlier things. And so sometimes if you know how a generator shrinks, you can set things up so that it shrinks a little more favorably. But especially when you're generating like sequences of events and there's some state that ties them together, it gets really, really hard. I think there might be some custom techniques, but like I said, like test.check doesn't have an API for supporting these things. If you want to do stuff at the low level and learn how test.check's implemented, you can certainly do whatever you want, just like in Clojure. But like I said, I don't know of a good API for letting people do really general stuff like that. So I think I'm out of time. I'm happy to take any questions for the rest of the conference. Thank you.